Hey guys, these are our notes about parent graphs. So we're going to be on slide 14 through 16 today. At the top of your paper, you can go ahead and put your title, Notes 4B.2.1 Parent Graphs. So we're going to look at transformation on parent functions today. We're going to look at a bunch of different types of functions, but the way that they are transformed is the same. So we're going to have our functions. We're going to have a times f of x minus h plus k. So f of x is just whatever type of function we have. The a value here is going to be some sort of stretch or flip if it's negative. The h is our horizontal shift. With h, you have to remember to change the sign. And k is your vertical shift. And with k, you get to keep its sign. So today, those are the three shifts we're going to be looking at, or three transformations on a parent graph. So we're going to look at, I think it's 7 parent functions right now. So the first one is linear. The parent function for a linear equation is f of x equals ax plus k. I know we normally use y equals mx plus b, but today we're just talking about the a is normally your slope. That's like your stretch. It changes it. It could flip it if it's negative. And then k is your vertical shift. So that's what moves it up or down to its y-intercept. So a linear equation just looks like a little line. And we're going to write down the domain and the range. So I'm going to write down domain and range like the first couple times, and then I'm going to start writing D and R. So the domain for a linear equation is just all real numbers from negative infinity to positive infinity. And the range is also all real numbers, negative infinity to positive infinity. So a line, there's no stipulations. The arrows go both directions. There's no asymptote, nothing like that. So it's just all real numbers for both the domain and the range. So remember, domain is the numbers you can plug in for x, and then range is the numbers you could get out for y. All right, the next one is a quadratic function. So a quadratic function is going to look like f of x equals a times parentheses x minus h squared plus k. And a quadratic function, when you graph it, looks like a parabola, so like a U shape. The domain for, I'm just going to use letter D, for a quadratic function is always, again, just all real numbers, just like a line. You can plug in any x that you want. But the range, range is your y value. Since there is a, like the vertex, the turning point, that's going to change your range. So if your a is positive and your arrows are pointing up, if you have a positive a, then your range is going to be from your k value to positive infinity. And if your a is negative, it's going to be opposite. It's going to be from negative infinity up until your k value, because your parabola would be going downwards like this. So the maximum you could go is whatever your k is. So your k is the y part of your vertex, and the range is your y values. Next one is cubic. Cubic's going to be really similar to, the equation part is going to look really similar to quadratic. A cubic equation is f of x equals a parentheses x minus h cubed plus k. The domain, again, is just all real numbers. You can plug in any number you want for your x. And the range on a cubic function is also all real numbers. It's like the line. The cubic function's little graph looks like this. The arrows just go both directions. Any domain, any range. All right, next one is exponential. So the exponential function, the equation's going to look like f of x equals a times b to the power of x minus h. They might not put parentheses around it, plus k. An exponential function, if it's a growth function, it's going to look like it's kind of flat, and then all of a sudden it's going to curve and kind of go upwards. The domain for a exponential function is just all real numbers. You can plug in whatever x values you want. You can plug in any number for x here. The range, on the other hand, is going to depend on if your a value is positive or negative. So if your A value is positive, then your range is going to be from your K value, which is actually where your asymptote is going to be. Is from your K up, but if your A was negative, then it's going to be going downwards. So it'd be from your infinity up until your K value, your asymptote. So your asymptote is your K value here. All right, a log function. We've done log functions very recently. So it was f of x equals a times log base b, whatever the base might be, x minus h plus k. So we already talked about domain and range. There is a domain restriction. It's based off of your asymptote. Log functions are the inverse of exponential. They start going straight up and then they kind of curve. They have a vertical asymptote, their h value. So your domain, if your x is positive, then it's going to be from your h value, it's parentheses because we can't include it, your h value towards positive infinity. But if you have a negative x value, it's going to be from negative infinity up until your h. The range, on the other hand, is just all real numbers. You can have any y value come out. The x square root function. So a square root function is going to look like f of x equals a times the square root. Normally they won't have the times. It'll just be a square root of x minus h under the radical plus k. A square root function looks like there's a starting point and then it just kind of curves. It doesn't have an arrow. This one doesn't go on forever. It just has an ending point. The domain for your square root functions depends on your h value. It's just from your h value to infinity. And then your range depends on your k value to infinity. So this point right here is your h and your k. So depending on where that point is, that's going to give you your arrow just goes towards infinity. Last one is absolute value. The absolute value function is going to look like f of x equals a absolute value bars, x minus h in the bars, and then plus k outside. An absolute value function is going to look like a V shape, like that. Your domain is just all real numbers. You could plug in anything for your x. But your range, on the other hand, depends on your k value, because it depends on where it stops. If your a is positive, it's going to be pointing up, so it's going to be from k going up. And then if a is negative, the v is going to be pointing down, so it's going to be from negative infinity up until your k. So I just want to remind you guys of what interval notation is again. So if you see parentheses, okay, the parentheses just means not included. It'd be like having a greater than or a less than symbol. And if you see a bracket, that means that that number is included. It'd be like having a or equal to underneath. So when we're looking at the domain and you see an asymptote, then you're always going to see a parenthesis with it. But with like the parabola and the absolute value ones, those ones have brackets because it's included. There's no asymptotes, because asymptotes you get really close to but never touch. All right, let's go do some examples. So let's go to page 39 of our workbook. This is unit 4B. Example number 1 on page 39 says, compare the graphs of the exponential functions a of x equals x e to the power of x plus 2, b is equal to e to the power of x plus 2, cross off letter c, and then d is equal to 2 times e to the power of x. Compare each graph's x and y-intercepts, domain and range. Those are the parent function, f of x equals e to the power of x. And then determine, we're not going to do that last part. It's number 5 on here, so we're just going to cross that one off. All right, so the first thing it says is to graph each of the functions on a graphing calculator. So notice this one basically has an h of 2, this one has a k of 2, and this one has an a of 2. So we're just going to look at what those different things do to your graph, okay? So here is the normal e of x, e to the power of x. That's what the graph looks like. Here is if I have the +2 in the exponent, so that's an h. So h moves your graph left and right. Since it's +2, it moves my graph to the left. Here's if I had a k value of 2, that moves my graph up 2. And here's if I had an a value of 2. It stretches it so it just goes up faster. So what we're going to do is look at these 3 graphs right here. So here is where there's an h of 2. So here's original. H of 2, k of 2, a of 2. All right, so what we're going to just write down, number 1, we're just going to say a of x moves left 2. B of x moved up 2, and then d of x, because we're not going to look at c, just as a stretch by 2. So we're going to compare the domains and the ranges. So if you remember, this is an exponential, e to the power of x. So when we talked about exponential domains, okay, here's exponential domains. Your domain is always going to just be all real numbers. So both of them, all 3 of them are all going to have the same domain of all real numbers. Then the range just depends on your k value. So if it has a k value, whatever the k value is, that's what's going to change your domain or your range. So we're going to look at domain. All of them are going to have the same domain. Just negative infinity to positive infinity for all of them. And then the range depends on your k value. So for this one, there was no k, and for this one, there was no k. That just means your k is 0. So that means that those ones are going to have a range from 0 to infinity. Oh, it's a parenthesis, because there's an asymptote. 0 to infinity. That's for a of x and d of x. But b has a k value of 2, so its domain is going to be from 2 to infinity. Then just says compare the y-intercepts. So I'm going to write down the y-intercepts for all of them. I'm going to write it down now so I can go look at it, remember. So a, b, and d. So a of x, the y-intercept is at 7.389. That's actually e squared. Here's e squared. Is that number right there? 7.3829. So it's actually e squared. And then here's the y-intercept is at 3. Here the y-intercept is at 2. So e squared, 3, and 2. Then it says determine and compare the y or x-intercepts. So when you look on your graph, here's the x-axis right here. So this graph, so it gets really, really close to the x-axis, but does it ever actually touch it? Cross it? No, because there's an asymptote, and the asymptote for these two is at 0. The asymptote for this one is at 2, so they will never actually touch or cross the x-axis. So there's actually no x-intercepts. And that's because of the asymptotes. All right, let's flip it over to example number 40. It says the graph shows a parent quadratic function x squared. So that's this one right here, f of x. And 2 quadratic functions g of x and h of x. So here's h of x. Here's g of x. It says they're derived from it. Use a maximum, minimum, or minimum point from the quadratic functions to derive their equations and write their functions in the form that indicates the transformations of the parent function, then describe what transformations they underwent to result in the transformation. We're not going to do that describing part. We're not going to write it down. At least we can maybe talk about it, but we're not going to write the part down. Okay, so we're going to write the equation. So we'll do g of x first. Okay, so what you want to do is you need to identify 2 points. You need to know what the vertex is, and then you just need one other point. So I'm going to use this point right here because it has a 0 in it. So this vertex point, notice that you go right 1, down 1. So that means this point is at 1, negative 1. And this point over here is at the point 0, 1, because we didn't go up or down at all, and then we went right 1. Okay, so we're trying to do g of x right now. All right, so the equation for quadratic is a parentheses x minus h squared plus k. We actually already know we're plugging in 3 things. We're plugging in a, h, and k, and we actually already know 2 of the 3 things we're going to plug in. We actually know h and k. H and k is your vertex. This other point we found, we're just going to say that that point is x and y, and we're going to use it to find h. Well, y is really just your g of x, so that's number 1. A is what I'm going to try to find. X is the number 0, minus h is 1, squared plus k is negative 1. So I'm just going to go ahead and solve for a. So 1 equals a times negative 1 squared plus negative 1. I'm going to go ahead and add 1 to both sides. So I get 2 equals a times negative 1 squared is just 1. So a times 1 is just a. So that means a is equal to 2. So for g of x, the equation is going to be a is 2, x minus h is 1 squared plus k, which is minus 1. So I'm just going to write a minus 1. So that's the equation for g of x, the yellow one. So the transformations made was it was stretched by 2. It was moved right 1, even though it's minus, and then down 1. So we moved right 1, down 1, and then it was stretched by 2. All right, let's go ahead and do the green one now, my h of x. So for h of x, all right, so for h of x, we're going to do the same thing. A parentheses x minus h squared plus k. We're going to identify the vertex. So the vertex here, we go left 1, so negative 1, and then up 2. So this is the point, negative 1, comma 2. And then we just need any one other point. So I'm just going to use this point down here. This would be 0, negative 1. So again, we already have 2 of the 3 things we know. We have an h and k, that's the vertex, and then we have x and y. So we know h and k, we just need to find a. So to find a, we're just going to use this other point. H of x is my y, so that's negative 1 equals a, parentheses, x is 0, minus h is negative 1. Well, when I subtract a negative 1, that turns plus 1, squared, and then k is plus 2. So I have negative 1 equals a times 1 squared plus 2, subtract 2 on both sides, I get negative 3 equals a times 1, which is just a. So a is equal to negative 3. So my equation for h of x, my a is negative 3, x minus h was negative 1, so when I subtract a negative, I'm going to add 1, and then squared plus k, which was 2. So here's my equation for the one I have in green. So if I describe, we're not going to write them down, but we'll describe them. Negative means that it's flipped. That's why it's upside down. And then 3 means it's stretched by 3. The smaller the number, the skinnier the parabola is. The bigger the smaller it is, like a fraction, the wider the parabola will be. And then I went left 1 and then up 2. So that's how we get the transformations. All right, last example, number 3. It says identify the transformations to the parent function f of x equals log x that result in the function g of x equals 1 plus 2 times log. I just need you guys to cancel out whatever number's in front of it. I think it was a 3. X plus 4. Describe the effect on the transformations on the domain and range. Finally determine the y-intercepts. We're not going to do the y-intercepts part though. All right, so we're just going to identify the transformations and then we'll give the domain and the range. So there's one thing I don't like about g of x right now. I don't like how it says 1 plus 2 times. We're going to rewrite it as 2 times log x plus 4 in parentheses, and then this 1 that used to be at the end, I'm actually going to, or at the front, I'm actually going to put it at the end, because now I can easily see my a, h, and k. So I can describe what they do. So I have a stretch by 2. Then my 4 is my horizontal shift. That means it moves left and right, but it's plus 4. It's the opposite. It's actually going to move left 4. And then my k is a vertical shift, so I'm actually going to move up 1. It gets to keep its sign. So with log function, so what you have to remember about a log graph is it starts, it goes up, and then it curves. Right here you have an asymptote. That asymptote is at your h value. So your domain, your x's that you can plug in, your x's can only be the ones on this side of the graph. So my domain, it's an asymptote, so I can't include it, is at the number -4, because h, you have to change the sign, to infinity. And my range for a log function is just always all real numbers from -infinity to +infinity. So when we describe what happens, we have a stretch by 2, move left 4, move up 1. Those are the transformations. And the domain, what that does, since you move left 4, that just takes your domain and moves it left 4 to -4, but the range is still just all real numbers. And that's it. We're going to put these onto slide 14, 15, and 16, and then your homework is page 43 in the workbook.